Right, so we'll be going through section 8.2 today, and it basically consists of hypothesis testing again. And the topics that we'll be going through are basically maximum likelihood decisions and maximum a priori decisions, right? And these are the problems that we'll be going through. Right, so basically the job of the MAP test is basically to divide the basically output space into two sets, which are A0 and A1, right? So basically, if an we need to decide, basically we have a set of outcomes, right? And we have to decide where each, in which set each outcome will lie, right? So we'll basically be conditioning we'll basically try to find the conditions for basically each outcome to belong to the set a0 or a1, right? And a1 is simply a0 complement. So basically, and we have to do this while trying to minimize the probability of error. So s will belong to a0 if p of s given h1 into p of h1 is less than equal to p of s given h0 into p of h0, right? So we're basically trying to reduce the error and basically get an A naught, which will basically be as close to the hypothesis H naught as possible, right? So this should also be pretty intuitive that S will belong to A naught if P of S intersection H naught is greater than equal to P of S intersection H1, right? Right. So basically, and if the outcome is basically any random vector x, the MAP hypothesis turned out to be if x is discrete, x will belong to A naught if p of x given h naught of x divided by p of x given h1 of x is greater than equal to p of h1 divided by p of h naught. This is essentially the same statement as we mentioned above, just that instead of any sample output s, we have a random vector x, right? And if this is continuous, we'll basically be working with the uh, PDF small f, which is basically f of x given h naught of x divided by f of x given h1 of x is greater than equal to p of h1 by h naught, and x belongs to a1 otherwise, right? So next is basically the maximum likelihood decision rule, and this also basically the goal is simply to minimize the probability of error. But in the maximum likelihood decision rule, we basically do not want to depend upon the a priori probabilities, which are p of h naught and p of h1, right? So this simply conditions on the basically conditional probabilities, and it says that s will belong to a naught if p of s given h naught is greater than equal to p of s given h naught. So basically this is the same as the MAB test, and basically instead of the a priori probabilities p of h naught and p of h1, they're both basically equal in this, right? So if you look at basically theorem 8.6, if the experiment produces a random vector x, the discrete decision will be x will belong to a naught if p of x given h naught of x divided by p of x given h1 of x is greater than equal to 1, and if it is continuous, basically x will belong to a naught if f of x given h naught of x divided by f of x given h1 of x is greater than equal to 1, right? So basically this is similar to the MAP test, except that we assume p of h naught and p of h1 to be equal, right? So that's an easy way to get the maximum likelihood decision condition from the maximum a posteriori decision, and that is just to basically take note that maximum likelihood just uses the condition by assuming that p of h naught is equal to p of h1, right? So I hope that's okay with everybody. Let's start with the problems then. So the first problem that we're looking at is example 8.4, And it says the noise voltage in a radar detection system is a Gaussian 0 1 random variable n. When a target is present, the received signal is x is equal to v plus n volts with v greater than equal to 0. Otherwise, the received signal is x is equal to n volts. Periodically, the detector performs a binary hypothesis test with H0 as the hypothesis no target and H1 as the hypothesis target present. The acceptance sets for the test are A0 is equal to x less than equal to x0 and A1 is the set x greater than x0. Draw the receiver operating curves of the radar system for the three target voltages V equal to 0, 1 and 2 volts. Alright, so we're basically given the received signal x looks like, and if a signal is received, if the target is present, it will be basically equal to some value v plus Gaussian noise, and where v is greater than equal to 0. And if the target is not present, it will basically be simply equal to Gaussian noise, right? And we're also given what the acceptance sets looks like, and we have to draw what the ROC curves will look like, right? So basically the ROC, to draw the ROC, what we need is basically the probability of false alarm and the probability of miss. So false alarm will basically be if there is no target and we still end up getting basically the set A1, the outcome will belong to the set A1 even though there is no target, right? So that is basically our false alarm. And miss will be if the target is present but we still end up getting A0, right? So basically miss is the probability of A0 given H1, and false alarm is basically the probability of A1 given H0, right? Right, so basically to draw the ROC, we have to find basically what the probability of false alarm and probability of miss will look like, right? So we're given everything about basically the distribution of x for each of the hypotheses, and we have to find what p miss and p of false alarm will look like, right? So we're given that if there is no target, which is the hypothesis H0, x will be equal to n, which is a Gaussian random variable with the mean 0 and standard deviation 1, right? And under the hypothesis H1, which is basically that the target is present, x will be equal to v plus n, which will be a Gaussian random variable with the mean v and standard deviation 1, right? Since it's just a shifted version of the standard Gaussian, right? So what we know is that the probability of miss is p of a0 given h1, right? And what were the conditions for a0 and a1? So the sets a0 and a1 were defined as basically a0 is equal to x less than equal to x0, and a1 is equal to x greater than x0, right? So what will be the probability of a0 given h1? It will be basically the probability that x is less than equal to x0 given h1, right? So basically we can think of this in terms of the Gaussian, the standard Gaussian CDF, right? So that will basically be equal to psi of x0 minus the mean, which for this situation will be equal to v, since basically the distribution of x when h1 occurs is the Gaussian v comma 1, right? So this will basically be equal to psi of x0 minus v divided by 1, right? And similarly, basically the probability of false alarm, which is equal to p of a1 given h0, which will be equal to p of x greater than basically x0 given h0. And basically we know when h0 occurs, x is simply equal to n, and basically the Gaussian random variable has mean 0 and standard deviation 1, and this is basically x greater than x0 will be basically 1 minus x less than equal to x0, right? So here we can again use the Gaussian normal CDF, right? So this will be basically equal to 1 minus psi of x naught minus 0 divided by 1, right? So that will be equal to 1 minus psi of x naught, right? So now we basically derived what the probability of miss and probability of false alarm would look like, right? And we are given basically different values of v for which we have to evaluate, right? Uh, right, so basically this can be done in any program, I guess. And I guess this is all we had to, like, you can look into the plots later, but I guess this is where we'll be moving forward, right? So I hope that's okay with everybody. Let's move forward to the next problem, which is problem 8.2.1. And the question says, in a random R, the number of call attempts n at a telephone switch has a Poisson distribution with the mean of either alpha naught hypothesis h naught or alpha 1 corresponding to hypothesis h1 for a priori probabilities p of hi. Find the MAP and ML hypothesis testing rules given the observation of n, right? So we're basically given that n is the number of call attempts at a telephone switch, and n has a Poisson distribution with a mean of either alpha naught if the, which is basically the distribution of n if the hypothesis h naught occurs is basically Poisson distribution with mean alpha naught, and but if hypothesis h1 occurs, it is basically Poisson distribution with the mean alpha 1. And given a priori probabilities p of hi, we have to find the MAP and ML hypothesis testing rules, right? Right. So we basically have to so we basically have to decide on the sets A0 and A1 using both MAP and the ML testing rules, right? So basically, let's start with the MAP rule, and so basically n will belong to A0 if P of n given H0 of n divided by P of n given H1 of n will be greater than equal to P of H1 by H0, and P of n given H0, we know that is a Poisson distribution with the mean. So they've changed alpha to lambda here, it seems like, right? So anyway, that's trivial. So we know that n is basically a given h naught. N is basically a Poisson random variable with the mean lambda naught, right? And given h1, n is a Poisson random variable with mean lambda 1, right? So basically, Poisson distribution with the mean lambda naught and lambda 1, right? So P of n given hi of n will be equal to lambda I to the power n e raised to the power minus lambda I divided by n factorial, right? So if we replace this in the MAP condition rule, right? Basically n factorial will get cancelled, and we'll be left with the condition that n will belong to A naught if lambda naught divided by lambda 1 raised to the power n into e raised to the power minus of lambda naught minus lambda 1 is greater than equal to p of h1 divided by p of h naught, right? So now we can just take log base e on both sides, right? So we'll basically get n times ln of lambda naught by lambda 1 plus basically minus of lambda naught minus lambda 1 is greater than equal to p of ln of p of h1 divided by p of h naught, right? So we'll take minus of lambda naught minus lambda 1 to the other side, and that will basically be equal to ln of lambda naught by lambda n times ln of lambda naught, right? N times ln of lambda naught by lambda 1 is greater than equal to lambda naught minus lambda 1 plus ln of p of h1 divided by p of h naught, right? So then we'll multiply by minus 1 on both sides, and minus of ln of a by b is equal to ln of b by a, right? So we're going to do that as well. So this will be minus of n times ln of lambda naught by lambda 1 is less than equal to lambda 1 minus lambda naught minus ln of p of h1 divided by p of h naught. Now, now basically doing the ln of a by b thing, right? We'll have n times ln of lambda 1 by lambda naught is less than equal to lambda 1 minus lambda naught times lambda 1 minus lambda naught plus ln of p of h naught divided by p of h1, right? So n should be less than equal to lambda 1 minus lambda naught plus ln of p of h naught divided by p of h1, this whole thing divided by ln of lambda 1 by lambda naught, which is what the second last statement says, right? So n will belong to a naught if n is less than equal to n map or n star, which is equal to lambda 1 minus lambda naught plus ln of p of h naught divided by p of h1 divided by ln of lambda 1 by lambda naught. And yeah, so basically if n is less than equal to this, it will belong to a naught, and n will belong to a1 otherwise, right? So now we've obtained what the condition for the MAP rule will be, right? And now we need to find the condition for the maximum likelihood rule, right? So we know that maximum likelihood is similar to maximum a posteriori rule, except that it doesn't assume about the a priori probabilities p of h naught and p of h1, but instead takes them to be equal, right? So if we just set p of h naught equal to p of h1 in this expression, which will basically make the ln term in the numerator basically be equal to ln of 1, which is equal to 0, right? So yeah, by doing that we can get basically the maximum likelihood condition, and that will be n will belong to a naught if n is less than equal to n ml or n star, which is equal to lambda 1 minus lambda naught divided by ln of lambda 1 by lambda naught. And yeah, so basically if n is less than this term, it will belong to a naught, otherwise it will belong to a1, right? So right, so basically given the distribution of n given either h naught or h1, we basically had to find the MAP and the ML hypothesis testing rules, right? And we basically found the conditions for a naught and a1 using both MAP and ML rules, right? So this is done. I hope that's okay with everybody. Right, so let's move on with the next problem, which is problem 8.2.4. And the question says, in the radar system of example 8.4, the probability that a target is present is P of H1 equal to 0.01. In the case of a false alarm, the system issues an unnecessary alert at the cost of C10 equal to 1 unit. The cost of a miss is C10 equal to 10 raised to the power 4 units because the target could cause a lot of damage. When the target is present, the voltage is x is equal to 4 plus n, a Gaussian 4,1 random variable. When there is no target present, the voltage is x is equal to n, the Gaussian 0,1 random variable. In a binary hypothesis test, the acceptance sets are a0 equal to x less than equal to x0 and a1 equal to x greater than x0. What is x0 equal to x MAP? The decision threshold of the maximum a posteriori probability hypothesis test. What are the error probabilities PFA and PMIS of the MAP test? Right, okay. So we're given that the problem is same as example 8.4. So let's go through example 8.4 once again, right? And right, so in example 8.4, we had if the target is present, then x is equal to v plus n, which for our question is now 4 plus n, I suppose. And if the target is not present, it is equal to x is equal to n, and basically the acceptance at a naught is x less than equal to x naught, and a1 is x greater than x naught, right? So I think we have all the information here, right? So when target is present, x is equal to 4 plus n, and when the target is not present, the basically x is equal to n, and a naught is basically the set when x is less than equal to x naught, and a1 is the set where x is greater than x naught, and we have to find x naught equal to x MAP, and the probability of false alarm and the probability of miss for the MAP test, right? So basically, if you observe, I don't think we have anything to do with the costs, right? So I think that's just some additional information in the question, but I don't think we'll be using that, right? So right, so for the first part, we have to find x naught equal to x MAP, right? So we're given that given a h naught, x is a Gaussian with mean 0 and standard deviation 1, and given h1, it is a Gaussian with mean 4 and standard deviation 1, right? And so using the formula for the MAP hypothesis test, we have x will belong to a naught if f of x given h naught of x divided by f of x given h1 of x, which is equal to e raised to the power minus x squared divided by 2 divided by e raised to the power minus of x minus 4 whole square divided by 2, and this whole term should be greater than equal to p of h1 divided by p of h0, not just the denominator, right? So that appears to be a typo, so I hope everybody understands what I'm saying, right? uh, right, so x belongs to a naught if f of x given h naught of x divided by f of x given h1 of x, which is equal to e raised to the power minus x square by 2 divided by e raised to the power minus x minus 4 whole square by 2, and this whole term is greater than equal to p of h1 divided by p of h0, right? So we're given what p of h1 is in this question, right? So basically, since a target probability, so yeah, so x will belong to a naught if right, so basically we'll just simplify this expression, right? Basically x will belong to a naught if e raised to the power minus x square by 2 divided by e raised to the power minus x minus 4 whole square by 2 is greater than equal to p of h1 by h naught, right? So basically simplifying the term on the left hand side, we get e raised to the power x minus 4 whole square minus x square by 2, so this is a square minus b square, right? So that will become e raised to the power minus 4 x minus 2 is greater than equal to p of h1 divided by p of h naught, right? So now we'll take ln on both sides, so we'll get basically minus 4 times x minus 2 should be greater than equal to ln of p of h1 divided by p of h naught, right? So basically taking minus 1 by 4 to that side, we'll get basically x minus 2 should be less than equal to minus 1 by 4 ln of p of h1 divided by p of h naught, and taking 2 to the other side, basically we'll get x should be less than equal to 2 minus 1 by 4 ln of p of h1 divided by p of h naught, right? So basically, which is this is exactly the condition in the second last line, right? So x belongs to a naught if x is less than equal to x of MAP, which is equal to 2 minus 1 by 4 ln p of h1 divided by p of h naught, and we're given p of h1 and thus also p of h naught, right? So basically putting in the values of 0.01 and 0.99, we'll basically get that x will belong to a naught if x is less than equal to 3.15, and otherwise x belongs to a1, right? Right, so we found what the condition for MAP is, and for the next part we have to find the probability of false alarm and the probability of miss, right? So the probability of false alarm will be basically the probability that uh, false alarm, so basically the probability of a1 given h naught, right? And what was the condition for a1? X greater than x naught, right? So that will be so probability of false alarm will be I think this should be just greater than instead of greater than equal to, and P of miss will be less than equal to, right? So there appears to be a typo here again. So the probability of false alarm will be equal to the probability that x is greater than x map given h naught, right? So we can basically use the standard normal CDF or the standard complementary CDF, which is the Q function, right? So given h naught, the distribution of x is standard Gaussian 0, 1, right? But this is basically x is greater than x MAP, which will be equal to 1 minus probability of x less than equal to x MAP, right? So that will be equal to 1 minus psi of x MAP, or basically which is equal to q of x MAP, since the mean is 0 and standard deviation is 1, right? And we all know the values of we know the value of x MAP, right? So this will turn out to be equal to, so the q, basically evaluating from the table of q function and standard normal CDF function, we'll get the value of this to be equal to 8.16 into 10 raised to the power minus 4, right? And similarly, what will be the probability of miss? It will basically be the probability that x is less than equal to x MAP given that h1 occurs, right? So given h1, it is a Gaussian, x is basically a Gaussian with mean 4 and standard deviation 1, right? So this will be equal to basically psi of x MAP minus 4 divided by 1, which will be equal to 1 minus psi of 0.85, which will be equal to 0.1977, right? So you don't have to bother with the exact values, I think. But yeah, I hope everybody is okay with this, right? So let's move forward to the next problem. Right, so the next problem is problem 8.2.6, and the question says some telephone lines are used only for voice calls, others are connected to modems and used only for data calls. The duration of a voice telephone call is an exponential random variable v with expected value e of v equal to 3 minutes. The duration of a data call is an exponential random variable d with expected value e of d equal to mu d equal to 6 minutes. The null hypothesis of a binary hypothesis test is h naught. A line is used for voice calls. The alternative hypothesis is h1. A line is a data line. The probability of a voice line is P of V equal to 0.8. The probability of a data line is P of D equal to 0.2. A binary hypothesis test observes n calls from one telephone line and calculates mn of t, a sample mean of the duration call. The decision is h naught if mn of t is less than equal to t naught minutes. Otherwise, decision is h1. A. Use the central limit theorem to write a formula for the false alarm probability as a function of T naught and n. B. Use the central limit theorem to write a formula for the miss probability as a function of T naught and n. C. Calculate the maximum likelihood decision time T naught equal to T ml for n equal to 9 calls monitored. And D. Calculate the maximum a posteriori probability decision time T naught equal to T MAP for n equal to 9 calls monitored. Right, so we're given basically that a line can have voice calls or data calls. Voice call, basically, the duration of the voice call is an exponential random variable v with the mean 3 minutes, and basically the duration of a data call is an exponential random variable d with mean 6 minutes, right? And h naught is the hypothesis that the line is used for voice calls, and h1 is the hypothesis that the line is a data line, right? And the probability of voice calls is 0.8, the probability of it being a data line is 0.2, and the binary hypothesis test basically observes n calls and calculates the sample mean mn of t, and the decision is h naught if mn of t is less than equal to t naught. So a naught is basically equal to mn of t less than equal to t naught, right? And otherwise the decision is h1, right? So we have to use a central limit theorem to find the probability of false alarm and the probability of miss, and we have to find basically the maximum likelihood decision time and the maximum a posteriori probability decision time, right? So we're given everything about the question, so let's move forward with the solution, right? So given h naught, we know that the basically sample mean has expected value which will be equal to e of v divided by n, which is equal to 3 over n, right? And the variance will be variance of v divided by n, which will basically be equal to 9 over n, since it's an exponential random variable, right? So, and given h1, we know that mn of t has expected value e of d over n, which is equal to 6 over n, and variance equal to variance of d over n, which will be equal to 36 over n, right? Right, so now we know everything we need to know about basically the sample mean conditioned on either h naught or h1, right? And the probability of false alarm will basically be equal to the probability of a1 given h naught, right? And basically a naught was defined as mn of t less than equal to t naught, right? So a1 is basically mn of t greater than t naught, right? So the probability of false alarm is basically equal to p of mn of t greater than t naught given h naught. And we know basically that mn of t in this situation has mean equal to 3 over n and variance equal to basically 9 over n. So now we're going to basically subtract and divide basically to get to a form closer to central limit theorem, right? Right, so actually the expected value of mn of t will not be e of v by n or e of d by n, it will actually be equal to e of v and e of d, if I'm not wrong. Yeah, because sample mean has the same mean and variance gets divided by n, right? So, right, again I think there's a typo. So mn of t will have, given h naught, mn of t will have expected value equal to e of v, which is equal to 3, and variance equal to variance of v by n, which is equal to 9 by n. And given h1, mn of t will have expected value equal to e of d, which is equal to 6, and variance equal to variance of d by n, which is equal to 36 over n, right? Right, so we'd basically, where were we before this? We'd basically, we'd basically written the formula for P of false alarm, right? Which will be equal to P of mn of t greater than t naught given h naught, right? So now basically to get this to a form where we can apply the central limit theorem, we'll basically subtract the mean and divide by the standard deviation on both sides, right? So we'll have, and this is given h naught, right? So the mean will be 3 and variance will be 6 over n. So, and thus standard deviation will be root over 9 over n, uh, 9 over n, not 6 over n, right? So this will be equal to probability that mn of t minus 3 divided by root over 9 over n is greater than t naught minus 3 divided by root over 9 over n, right? So now we can basically apply the central limit theorem, and this will be basically equal to 1 minus psi, or which is equal to q, right? So they brought root n to the numerator, right, and divided by 3. So this will basically be equal to q of root n times t naught by 3 minus 1, which is the same as t naught minus 3 by divided by root over 9 over n, right? And yeah, so next what we have to find is basically use central limit theorem to write a formula for the miss probability, right? So miss probability will be the probability of a naught given h1, right? And a naught is basically the event where mn of t is less than equal to t naught, right? So the probability of miss is basically the probability of mn of t less than equal to t naught given h1, and we know that given h1, mn of t has expected value equal to 6 and variance 36 by n, right? So again, once again, subtracting the mean and dividing by standard deviation on both sides, what we'll get is basically p of mn of t minus 6 divided by root over 36 over n is less than equal to t naught minus 6 divided by root over 36 over n, right? And basically again and this will simply be equal to the psi function, right? And once again taking root n to the numerator and dividing by 6, what we'll basically get is basically psi of root n times t naught by 6 minus 1, right? So for the C part, we have to basically calculate the maximum likelihood decision time t naught equal to tml for n equal to 9, right? Right, so now basically to I think C part is maximum likelihood, right? Right. Right. So basically, to evaluate the maximum likelihood or even the maximum a posteriori condition, we'll basically have to know the distribution of mn of t, right? And which we do not know as of now. We only know that mn of t is basically the sum of the sample mean of basically uh, the sample mean of the duration of call, right? And the duration of call is an exponential random variable, right? So basically, mn of t can be written as some random variable yn over n, where yn is the sum of independent and identically distributed exponential random variables, right? So basically, and we know that basically the sum of IID exponential random variables is basically an Erlang random variable, right? And right, so basically we know what kinds of exponential random variables are being used for each of the hypotheses, right? So under the hypothesis H naught, yn is an Erlang random variable with parameters n and lambda naught equal to 1 over the expected value, which is equal to 3, right? Given H naught, E of V is equal to 3. And under the hypothesis H1, yn is an Erlang random variable with parameters n and lambda 1 equal to 1 over E of D, right? Yeah, 1 over E of D, which is equal to 1 over 6, right? So mn of t is equal to yn over n, and it is a scaled version of yn, which we found to be an Erlang random variable, right? So mn of t will also be an Erlang random variable, but now with parameters n and n lambda I, right? So we essentially found what the PDF of mn will look like given either of the hypothesis, right? So basically f of mn of t given hi of t is basically equal to n lambda I raised to the power n into t raised to the power n minus 1 into e raised to the power minus n times lambda I t divided by n minus 1 factorial for t greater than equal to 0 and 0 otherwise, right? So now the ML rule is basically t will belong to a naught if basically f of mn of t given h naught of t divided by f mn of t given h1 of t is greater than equal to 1, right? So basically f mn of t given h naught of t divided by f mn of t given h1 of t will basically be equal to, so you if basically if you divide these terms, basically the n term in the numerator will get cancelled, the t term in the numerator will get cancelled, the n minus 1 factorial term in the denominator will get cancelled, and what will basically be left is lambda naught divided by lambda 1 raised to the power n into e raised to the power minus n times lambda naught minus lambda 1 into t, and this should be greater than equal to 1. And if this is greater than equal to 1, basically t will belong to a naught, otherwise t will belong to a1, right? And if you basically take ln and simplify this, what we'll get is that t should be less than equal to t ml, which is equal to ln of lambda naught divided by lambda 1 divided by lambda naught minus lambda 1. And we already know the values of lambda naught and lambda 1, right? So this will be basically equal to 6 ln2, which is equal to 4.159, right? Right, so I guess that should be okay, right? So for the next part, we have to do the same thing, but basically with the MAP decision rule. So basically the PDF remains same, just that the condition is now basically that it should be greater than equal to P of H1 divided by P of H naught. So basically lambda naught divided by lambda 1 raised to the power n into e raised to the power minus n times lambda naught minus lambda 1 into t should be greater than equal to P of H1 divided by P of H naught. And we're also given what P of H naught and P of H1 are, is the probability of D and probability of V, right? So probability of H naught is equal to probability of V, which is equal to 0.8, and probability of H1 is equal to probability of D, which is equal to 0.2, right? So once again, taking this expression will basically simplify to that t will belong to a naught if t is less than equal to t map, which is equal to ln of lambda naught by lambda 1 minus 1 by n times ln of p of h1 divided by p of h naught, this whole term divided by lambda naught minus lambda 1, and replacing the values, this term basically simplifies to 6 into ln of 2 plus ln of 4 by n. And we're also given basically that the call n, basically 9 calls are monitored, so we can also replace the value of n, and thus we'll get t of map. T map is basically equal to 5.083. Right, so I guess we're done with this question. Right, so the next problem is problem 8.2.7, and the question says, in this problem, we repeat the voice data line detection test of problem 8.2.6, except now we observe n calls from one line and record whether each call lasts longer than t0 minutes. The random variable k is the number of calls that last longer than t0 minutes. The decision is h0 if k is less than equal to k0, otherwise the decision is h1. A. Write a formula for the false alarm probability as a function of T0, K0, and N. B. Find the maximum likelihood decision number K0 equal to KML for T0 equal to 4.5 minutes and N equal to 16 calls monitored. And C. Find the maximum a posteriori probability decision number K0 equal to Kmap for T0 equal to 4.5 minutes and N equal to 16 calls monitored. So what does this question say? So first of all, we have the same voice data line experiment as the previous question, but instead of observing the sample mean of call durations, we will instead be observing n calls from the line and record whether each call lasts longer than t0 minutes, right? And the random variable k is the number of calls that last longer than t0 minutes. If less than k naught calls last longer than t naught minutes, then we'll decide that the line is a voice line. But if more than k naught calls last than t naught minutes, then we'll decide that it is a data line, right? And we have to find basically the false alarm probability, the maximum likelihood decision number given that t naught is equal to 4.5 and n is equal to 16, and the maximum a posteriori probability decision number given that t naught is equal to 4.5 and n is equal to 16. Right, so I guess we have everything we need, and basically to find all of these, the false alarm probability, the ML decision, and the MAP decision, we first have to figure out what the distribution of K would look like, right? And right, so let's figure that out first, I guess. So K is basically the number of calls that last longer than t naught minutes, right? Yeah. So and we have to find the distribution of k conditioned on each of the hypotheses. So let's first think about a single call, right? So what is the probability that any call conditioned on h naught will last greater than t naught minutes, right? So what is essentially p naught equal to the probability that is greater than t naught given h naught, right? And we basically know that the call duration is an exponential random variable with the mean equal to 3, right? And So basically the probability that t is greater than t naught given h naught will be equal to e raised to the power minus t naught by 3, and conditioned on h1 is the probability p1, which is basically is a variable p1, which is basically the probability that t is greater than t naught given h1, and this is equal to basically e raised to the power minus t naught by 6, as the mean duration of data calls was equal to 6 minutes, right? Now we need to so now that we figured out what is the probability that any call lasts longer than t naught minutes, we can now, I guess, figure out the distribution of k, right? So basically we have the probability distribution of k conditioned on either of the hypothesis, and so basically any small k calls last basically longer than t naught minutes, right? And basically the PMF is P of k given hi of k is equal to nck pi raised to the power k into 1 minus pi raised to the power n minus k, right? So basically binomial PMF, because basically k out of the n calls last longer than t naught minutes with the probability p naught or p1, and the remaining calls basically last less than t naught minutes with probability 1 minus p naught or 1 minus p1, right? So I hope why why the distribution of k is will be a binomial PMF is okay with everybody, right? So now we need to figure out when the false alarm will occur, right? And the false alarm will occur if more than k naught calls basically last more than t naught minutes, even though it was a voice line, right? So the probability of false alarm is the probability that k is greater than k naught given h naught, and what will be the probability that k is greater than k naught? It will basically be the summation of the PMF of k summed over basically k naught plus 1 to n, right? Because there are total n calls, and we're conditioning it on h naught, right? So we'll be using p naught and 1 minus p naught as the probabilities of calls that last longer than t naught minutes and calls that last less than t naught minutes, right? So basically the probability of false alarm is summation k equal to k naught plus 1 to n nck p naught raised to the power k into 1 minus p naught raised to the power n minus k. Right, so I guess that should be okay with everybody. And for the second and third part, we have to find the maximum likelihood and the maximum a posteriori conditions, right? So for the B part, when we have to find the maximum likelihood decision rule, we have the condition that k will belong to a naught if p of k given h naught of k divided by p of k given h1 of k is greater than equal to 1, right? And what is p of k given h naught of k equal to, and what is p of k given h1 of k equal to? Right, so both of these will basically be equal to nck into p naught raised to the power k into 1 minus p naught raised to the power n minus k, and p of k given h1 will be equal to nck p1 raised to the power k into 1 minus p1 raised to the power n minus k. So when we divide the two, basically nck gets cancelled, and what remains is that basically p naught raised to the power k into 1 minus p naught raised to the power n minus k divided by p1 raised to the power k into 1 minus p1 raised to the power n minus k should be greater than or equal to 1, right? And so basically now I guess we simplify this, and on simplifying, what we get is that k will belong to a naught if k times ln of p naught over 1 minus p naught divided by p1 over 1 minus p1 is greater than equal to ln of 1 minus p1 divided by 1 minus p naught into n, right? And basically if we simplify, we can, I think it's simple enough. You all can simplify it further and put in the values of basically uh, yeah, so we're given the values of t naught and n, and we can use them to find the values of p naught and p1, and basically simplify this expression further, right? So t naught is equal to 4.5. So for t naught equal to 4.5, we will have p naught equal to e raised to the power minus 4.5 by 3, which is equal to e raised to the power minus 1.5, which is equal to 0.2231. And p1 will be basically e raised to the power minus 4.5 by 6, which is e raised to the power minus 0.75, which is equal to 0.47. So basically p naught is less than p1, and using this we can basically uh, simplify this to take care of the ln terms, right? Yeah, so basically on further simplification, what we have is that k will belong to a naught if k is less than equal to k ml, which is equal to ln of 1 minus p naught over 1 minus p1 divided by ln of p1 divided by 1 minus p1, the whole term, divided by p naught over 1 minus p naught times n, which is equal to 0.34 n. And yeah, so basically if k is less than equal to 0.34 n, it will belong to a naught, otherwise it will belong to a1. And putting in the value of n, which is 16, we get k ml is equal to 5.44. Right, so I'm basically skipping over the simplification and everything. I think you're all okay with simplifying ln and taking care of all those things, right? So let's move on to the next part. Yeah, so in this part we have to find the condition for the MAP test, right? And it'll be same as the ML test, except that it should be greater than or equal to P of H1 divided by P of H0, right? Uh, and basically when we simplify this, yeah, so when we simplify this, I think there will be an additional term which will basically be ln of p of h1 divided by p of h0, and p of h0 is equal to 0.8 and p of h1 is equal to 0.2. So dividing the two, what we get is 4. So there should be an additional term of ln 4, right? And I think statement 9 is incorrect. I think it's the same as from the last part, but there should be an additional ln4 term, which we can see in statement 10, right? And yeah, so basically on simplification, this comes out to be equal to 0.34 n plus 1.22, right? And for n is equal to 16, k map is basically equal to 6.66. So pretty similar to the last part. So I guess you're all okay with how to find the maximum a priori and the maximum likelihood conditions. Right, so that's it for today.